Okay, I guess we're on. Thank you all for coming. Welcome to the IDSS series. And today it's a pleasure to have with us Professor Sharma from University of Rochester, which I just found out that is actually a private university. And it's a pleasure to have you here. Professor Sharma was at the Xerox Corporation for many years. He's actually a product of our own department here, and the math department as well. And today he'll be talking about some of the research he's been doing on imaging. On the title of his talk is Imaging Arithmetic, Physics and UMath, and Physics plus Math. I don't know, but I don't know what it means exactly. If the greater means it's a complete, statement, or he'll tell us, I'm sure. Thank you for coming, and it's a pleasure. I guess
Thank you, Hamid. Thank you for inviting me, and thank you for the kind introduction. It's a pleasure to be back here after almost 10 years. I was last here for my graduation in December '96. So today I'm going to be talking about my work in imaging, and this is really sort of an inequality, which is I'd call a meta-inequality. And this is really referring to the fact that the union of the whole is greater than the sum of the parts. So if you look at the combination of physics and mathematics as it applies to imaging, it's greater than the sum of the parts. So that's the thesis. And if you're interested in more information on what I present over here, you can find relevant papers at my website over here. Before I begin this, I would like to talk a little bit about research activities within my group. And I'll give you a little bit of overview of what are the activities over here, so that if anybody is interested in talking to me after the presentation of what else I have ongoing in my lab, they can feel free to talk about that. I have roughly 4 areas of work within my group. One is the area in imaging systems and color science. This is largely what I'll be drawing from in the presentation today. This is color imaging, digital half-toning, performance evaluation, design of imaging systems. Part of this extends what I did in my graduate study over here and continues further, and also relates to work which I did at Xerox. The second area of work is in the area of multimedia security, where you're concerned with exchange of multimedia data, and you want to be able to either guarantee that it has not been changed from the time that it was signed by somebody, or be able to locate where somebody has placed or is reusing your material, for instance. The work there primarily is in the area of steganography, steganalysis, and watermarking. The two new areas in which I have some recent work is one is in digital image and video processing. In particular, this is directly towards multi-camera sensor networks, where you have sensor networks of tiny cameras trying to work cooperatively to achieve a task, such as, for instance, surveillance, or maybe give you a feeling of telepresence in a given environment. And lastly, the area of bioinformatics or genomic signal processing. So if you are interested in any of these, please feel free to talk to me after the talk over here. So as I already mentioned, I'll be concentrating in this talk primarily on the first part over here of having to do with imaging systems. So before I go into this, I'll talk a little bit philosophically about physically motivated signal processing. So we live in a physical world which is governed by laws of physics. So here we have Newton's apple falling. You typically tend to codify these laws in the form of mathematical relationships. So you begin by describing how do you define this. So classic example in the case of the apple is F equal to mass into acceleration, the Newton's relationship for the relationship between force and acceleration. And once you have a codification over here, this really enables you to do new things. And that's where engineering comes in. So an example of this is you can solve problems in a novel way, which you might not be able to conventionally think about. So what I'm showing over here is an example of balancing an inverted pendulum. This is a tough problem in controls. You have a pendulum which is mounted on a trolley, and by applying a force to the trolley, you want to balance this. And the novelty of this entire system is that once you've gone through this process of codifying your understanding of physics in the form of a mathematical relationship and come up with appropriate equations, you can actually solve a problem of this type, which you did not think was otherwise feasible. So this really summarizes my thesis that if you take the union, and this is really a sort of happy union between physics and mathematics, that happens to be actually greater than the sum of the individual parts. What you'd individually accomplish through any of these would be much less than what you would accomplish by this. Now, why imaging? So I'll give an example over here. What exactly do I be imaging? That may be something which is not familiar to most people. So if you look at a typical system in which you're dealing with images, a system has an end-to-end chain. The chain begins with something where you're capturing an image. So you begin with some sort of capture or synthesis of an image. You then have a representation in digital form for the image, which you may communicate to the other end. And ultimately, you have a projection or some sort of display for the image. Now, these may vary in different types. For instance, in the case of a digital camera, you may be capturing this by means of a digital camera. In the case of a printed document, you'll be capturing this by means of a scanner, and so on. Likewise, over here, the display systems that you're using may also vary. We have a nice backlit LCD or DLP projection display over here. I cannot tell just by looking at it. But the key thing to note over here is that the interfaces with the physical world, when you're capturing images or we are displaying, you're actually interacting with the physical world. And this is where you typically refer to things as imaging. So what you're doing over here, or what you're doing over here, comes under the purvey, under the classification of imaging. And this, since it's a natural interface between the physical and the digital world, is a natural source for a rich class of problems which blend physical representation along with the mathematical representation. So you have a whole series of physically motivated problems that you have related to imaging. Examples of this are, for instance, demosaicing when you're capturing an image, descreening if you're capturing a document image, correction for white point in this process, which is what is going on in the process of capturing this image of this current scene and displaying it, and similarly, corresponding processing on the output side. Now, in order to support my thesis, what I'll do is I'll work through a case study, and I'll basically work through a case study of looking at show-through and document imaging as one of the examples which will illustrate this idea. And at the end, hoping if I have time, I will quickly summarize some other applications where the same kind of synergy between the physics and the math gives you a very stronger combination than what would be possible at each one. So this is roughly an outline of what I'll be talking about for the main part of this talk. I'll be talking about first the problem of show-through and duplex printing. This is a problem which you encounter commonly when you have duplex printed document. If you don't understand the terms, don't worry. Most of them should be pretty clear. This talk is meant to be fairly accessible. I'll then look upon this as an artifact and look at techniques for correcting this and really present an analysis of show-through, a linearizing simplification, and an algorithm for show-through correction. And the real novelty here is that this is really possible only through a combination of three elements: the physics, maths, and the engineering innovation. You can't really do this by just doing one without the others. I'll present experimental results on this, and then I'll really take a different tack on this and say, instead of viewing this as an artifact, why not view this as an opportunity? Is there something you can do with it? And present an example of show-through watermarking, which is a way of mimicking conventional watermarks. All of you have looked at a dollar bill and held it up to light, or $20 bill, and seen the watermark in there. So this is a way of mimicking conventional watermarks through this process of using show-through as an exploit. Present some samples for this as I go along. So what exactly is show-through? For some of you may be wondering that. So if you have a duplex printed document, when you look at it, you can see what is printed on the back side. I'll refrain from pulling out a hard copy sample in the interest of the people who are viewing this remotely, although they typically show this by means of a printed sample which shows this. So think of a document in which you have printing on front and the back side. If you scan this document in the scan of the front side, you will have a residual image of the back side, and vice versa, in the scan of the back side, you'll have a residual image of the front side. Now, this is really, so what's an example of this? Here's an example of this. This is a page on which this is the statement from Xerox printed on the one side, and on the back side is a map of the United States of America. And you can see that what you can see in this image is not only what is printed on the front side, but a residual image from the back side. And what is disconcerting about show-through is that unlike noise, there's also noise in this image in the process of capture. Unlike noise, this is a very structured degradation. So you see it very quickly, and you say this is something which is not there in the image. You also have a similar scan for the other side, if you look at the other side. And the thing to note over here is not only do you see the show-through in the white background, but you also see it in the light gray region of Texas. So show-through is not just in the white region, but you also have it in light regions. So that will turn out to be a key aspect later on. So what is the traditional solution to this? Before I go to the traditional solution, let's look at some of the physical characteristics of show-through. Firstly, it's low contrast. That's just because you're viewing something through paper rather than directly on. It's more visible in right regions of the front page, less visible in dark regions, particularly in black regions. You don't see any show-through at all. It's blurred in comparison to the printing on the front side. That's because light has to go through the paper in order for you to see this effect. And finally, it's transposed, which is the optical effect of image on the back side being transposed with respect to the image on the front side. Now, the traditional solution to this has been thresholding. You simply threshold the image and say pixels above a certain gray value, you're going to make them white. Now, that works very well for images which are purely text, but images which have grayscale in them, that solution does not work so well, because it also removes low contrast front side information. So what I'm showing over here is in my pictorial cartoon representation. This is really low contrast front side printing, and this is really show through. But when you do this thresholding to convert regions to white, not only do you convert the show through to white, but also this low contrast printing on the front side is lost in the process. So let's look at it from our example perspective. So this is, the example was constructed particularly to illustrate this, the dichotomy between the two sides. For the text side, thresholding worked really well. You don't see anything in the show through at all. Well, if you look at the image side, on the other hand, you'll see that though you eliminated the show through from the background, it's really become a little more pronounced in here in the light gray region of Texas. Sorry about drawing on top of it. I intended to draw that underneath. You try and see. The eraser works. But you can see that the show through which you could see over here is eliminated. And thresholding really offers you no solution to this problem. You can change the threshold, you can adapt the threshold, but the only thing that will happen is that the only time the show through will be eliminated is when you eliminate also the state of Texas. And some people might say that's a good thing, but that's not what you want to do in your imaging system, at least. So what I'm going to be talking today about is an image processing technique for show through removal. Now, in the absence of any other information, if you have just an image from one side, you cannot really distinguish whether what you're seeing is low contrast printing on the front side or is actually show through from the back side. However, in typical systems, you're obviously often scanning both sides. And when you have both sides, you can collate the two sides information to figure out what is show through. If there is a high contrast printing on the back side and you see low contrast on the front side, that's probably show through. If on the other hand, all you see is something on the front side, nothing on the back side, that's probably a result of just low contrast printing on the front side. So my goal will be to come up with a technique which takes scans of the images on the two sides and comes up with some algorithm for processing it to separate the two into the scans which you would receive if there was no printing on the other side. Now, a key observation here is not only do you need to be able to recognize what is show through, but you also need to be able to figure out what is the contribution over here of show through. Because if you recognize that something over here is show through, so say you recognize this is show through, and you want to eliminate it, well, in the white regions it's very easy. You can say that it's white, so I make it white. But what in the light gray region of Texas? You have to figure out what is the appropriate value to replace it with. That's where the physical modeling actually comes in. So in order to begin with this, I'll first begin with a very simple physical model for this process. So we can make a very simple high school level physical model for this process. You can think of the system as consisting of some kind of a scanner backing over here. This is the backing in your scanner that you have, or typically a white backing, on top of which you have laid your, on top of the scanner you've laid your paper with printing on both sides. So this is representing a sheet of paper with printing on both sides. There is printing on the front side, which you're actually scanning, and there is your sheet itself, and there's printing on the back side. Now, the optics, the way it's arranged is there's a lamp from which you're illuminating a document, and then you're capturing this light by means of a sensor. So this is composed of, if you think of the light coming at the sensor, to a first level of approximation, we can think of three components for that. There'll be a first component, which is the component which comes from the lamp, encounters the front side printing. So how do we model that? Well, we can model that as a transparency factor, which is spatially varying for the front side printing. Part of it gets scattered back by the paper. That's what makes paper look white. Paper scatters most of the light back at you, so it makes it look white. So There's one component which goes through the front side printing, gets scattered back by the paper towards you. The second component which goes all the way through the paper, encounters the printing on the back side, and is then scattered back, is reflected back to you through the backing. So what are the corresponding terms in the physical model for these two? If you think of F as denoting the front side in this subscript over here, and B as denoting the back side, then there are two components that I mentioned in the previous slide. Let me go back over here. The first side encounters the transmittance of the printing on the front side layer and the fraction of light that the front side that the paper scatters back. That is the product of these two terms. That's the first term. Then the second term is the term which goes all the way through the front side layer, goes through the paper, goes through the back side layer, is reflected by the backing and comes all the way back to you, again encountering each of these on the way back. So this is the term which encounters each of these things twice and the backing once, which is why you have the squares for these additional terms. So the term corresponding to the product of this and this is representing the second part of light that I talked about. Now this is a very simple model. It's discarding several higher order effects, but to a first order this is fairly close to the actual system. And the fact that when you scan the front side, the reflectance that you're seeing in scanning the front side actually depends on the back side printing is an indication of the show through. This is what you're seeing in the show through. So this dependence on TB square XY represents show through. We can think of the scan of the back side similarly and model it in a similar fashion over here. This is the equation for this. The only what you've interchanged is the front and the back side. F and B have been interchanged in this process. Rest of the equation is exactly the same. So now what we have is a system of equations which are two nonlinear equations in terms of these desired quantities TF and TB, representing the transmittances of the front and back side layer which you would like to recover. Now you could think of solving these two equations for these, but there are also two problems with these equations. Firstly, these are nonlinear equations, so a solution is non-trivial. Secondly, which is a bigger important problem, is that we've simplified here to the point where it's a little too simplistic. We've really simplified to the point where we assume that the interaction is purely pointwise. In reality, what happens is when the light goes through paper, it actually undergoes scattering in here in the paper. So at this point, we rely on the engineering and make a heuristic approximation. So first, I'll address this aspect of the nonlinearity, and then I'll see how you handle the non-pointwise interaction. So if we transform this equation into the density domain, density is defined as logarithm of normalized reflectance. So you take the reflectance of the front side layer divided by the reflectance for white paper with no printing on either side. Take the logarithm of that and take the negative of that. That's called density. The units may vary depending on what logarithm you choose over there. Then one can take these previous equations that we had over here. The case when there is no printing on the front and back side will simply correspond to SP square plus TP square RBK. These two terms go to unity. And what we get is a term like this, shown over here. And this you can interpret as, the first term you can interpret as what would have the density been if there was no printing on the back side. So if there's no printing on the back side, this is what you would have obtained. And the second term is really the contribution of show through, which is the logarithm of 1 minus this term over here, this long term shown over here. Now again, you can rely on the physical intuition from this problem to figure out what approximation to make. One thing that you note is paper, when you look at it and hold it up, looks quite different from transparency. Paper looks white, transparency is you see what's behind it. And that's because this term is much larger than this term. So both of these terms are bounded above by 1, but this term is much larger. The fraction of light that paper scatters back at you is much larger than the fraction of light which it actually transmits through. So this term over here is quite small as compared to unity. This term is bounded between, this is 1 minus transmittance square, is bounded between 0 and 1. So you can approximate 1 minus the logarithm of 1 minus x is logarithm of 1 plus x. This is a simple mathematical approximation. And you have a model over here, which says that what you've got in the density for your first front side scan is really the density you would have gotten if there was no printing on the back side, plus a term which is linearly related to 1 minus tb square xy, which I'm calling the absorptance of the backside layer in double-sided transmission. So it's somewhat non-intuitive, and the reason this is non-intuitive is because these two terms, this term over here and this term over here, are in density, whereas this is really in a totally different domain. This is really coming from the mathematical side of the problem, not from the physical side of the problem. From the physical side of the problem, you would never think of adding quantities which are of different dimensions and different types. But the mathematical part of the problem really indicates this is the way to do it. So this now gives us a linear simplification now. At this point, we have a system which says that the scan density is the desired density plus a small fraction of the backside absorptance. Now, the second aspect which I mentioned was the aspect that the interaction is not really pointwise that you're dealing with. And the way we can incorporate that in a model is by saying that instead of having this fraction over here dependent on the paper parameters, you replace that by a point spread function. So you model your system as being the front side scan density is the density you would have if there was no printing on the back side, plus this point spread function, which I'll refer to as the show through point spread function, convolved with the backside scanned absorptance. And I've made one more approximation over here, and the approximation I've made over here is that I've replaced my true absorptance for the backside with the absorptance based on the scan. And you can analyze this further and show that the effect that you have as a result of this is a second order effect and goes down. So it's a smaller effect that you have. This h of xy I will call the show through point spread function, and it's really representing the term that we had over here at the previous slide. And what's the implication of that? Well, this term we argued was a small term. So the show through point spread function will always be a fairly small value that we talked about. Now, if you have all the terms and you know everything, then you can think of show through correction. Why not just correct this front side scan density by taking the show through point spread function, applying it to the backside absorptance or estimate thereof, and subtracting it from what you got. Well, there's still one remaining problem, which is that alignment between the front and the back side is not something that you can assume is constant throughout. In fact, when you scan, there is typically a jitter in the motion of the scanner. So what you will have as the alignment at a given point will vary depending on position. Well, that's where the engineering approach comes in. And you can recognize that this problem really becomes now analogous to the problem of echo cancellation. Once you've made it linear, this is like you have a document echo in your document from the back side. And for echo cancellation, people have used adaptive filters for quite a while for doing this. So that's the solution we adopt. Actually, did not go forward. So the signal processing solution to this approach is really using adaptive filters. And for those of you who may not remember the time of hybrids in the telephone circuits, the way the conventional telephone circuit was organized and way it's still organized to a good extent is that between your home and the local exchange, there's just 2 lines. Whereas between exchanges, there are 4 lines. Now, if there are 2 lines, they carry both the signal coming to you and the signal going away from you. And what keeps them separated is a hybrid, which is meant to keep this signal from actually going back all the way over here. In reality, the hybrids are not perfect. So what you get is a small echo. When you are talking to somebody, you will get an echo going back to them from what they're speaking. Now, how is this handled? Well, for terrestrial circuits, you typically don't care because this echo goes back so quickly that the person can't distinguish it from the time they're speaking themselves. For satellite circuits, this echo comes at a time when it's almost half a second after you spoke, and that's very irritating. If you ever had a phone call overseas, which is routed on a satellite circuit, it's becoming less and less common these days because of fiber optic networks being all around. But you can hear that echo, and that's very irritating. So the way you handle this is by looking at this and saying this is really a scaled down version of this. So why not just estimate what scaling I need to do for this in order to cancel it? And not only is there a scaling, but there is also a delay depending on what is the path this takes in order to come back. So the conventional solution to this is to put an echo canceller, which will basically try and predict what part of this is echo and cancel this from this output. And the way you do that is that in regions where you estimate that the local caller, the local speaker over here, is not speaking, anything you have over here must be due to echo. So you adapt the filter to cancel whatever signal you have over here in situations where the person over here is not speaking. So with that background in echo cancellation for telephony, the problem that we talked about becomes exactly that. So you can look at an overview of the entire algorithm that I talked about. You take the front side, take the negative, normalize it by dividing it by the reflectance of the white regions, take the negative logarithm. That will give you the front side scan density. For the back side, you do something different. For the back side, you divide it by the reflectance and subtract from 1. That's giving you an estimate for the back side absorptance. And now you process these two images in this fashion. So you want a pixel over here. Say this current pixel is where you want to cancel the show through. So you estimate the show through for this by taking a local neighborhood and weighting that neighborhood by that adaptive filter to figure out what is the corrected show through corrected value. This gives you a corrected front side density. In addition, you do regions of what I refer to in analogy with the telephony of front side silence detection. These are regions where there's no printing on the front side. In this case, whatever signal you have must be coming from show through. And you, in these regions, you adapt these filter coefficients in order to minimize the error. And the adaptation follows a standard LMS algorithm. So this adaptive filter is essentially trying to estimate and track your show through point spread function. The estimate is the part which is that you don't know, and it varies from paper to paper that you're dealing with. And the tracking is the fact that it's going to, the alignment is going to change in different parts of the image. And I'll show this a little later in the experimental results. Already mentioned this filter is adapted in foreign talk. For the adaptation, we use the LMS algorithm, which is the most commonly used algorithm for adaptive filtering. We impose the non-negativity constraints on the coefficients. Again, this is because the coefficients are representing a physical function, which has to be non-negative. And we process the image in a serpentine fashion in order to maintain adjacency. So typical adaptive filters are applied on one-dimensional signals, where time ensures sequentiality. Whereas in our case, we are applying this on an image. And if you have a discontinuity in jumping from one scan line to another, you will not have the same coefficients. A fairly large support we use in order to allow tracking of relative misregistration between front and backside scans. And there is more recent work we've done on image registration, which tries to get away from that. So I think most people here would be familiar with LMS adaptive filtering. The way to think about it is that if you think of just a single case where you have a scalar value, then the true equation is represented over here. This is my front side scan density related to this. If there is no printing on the front side, the density will be 0. It will be the same as white. Logarithm of 1 is 0. So this would be 0. This is the term you would have. And what you're predicting over here for the back is this quantity over here, which is the difference between the true and the predicted values. You look at the squared error, that amounts to a term like this. And if you plot it, it looks like this. You want to adapt the coefficient in a direction in which it reduces E square. So if you're on this side, you want to reduce A. If you're on this side, you want to increase A. That's the rough goal. And the algorithm has appropriate conditions under which it's not been shown to converge, but is experimentally seen to converge. And you always take small steps so that you don't overstep the bounds and don't oscillate. So now, okay, I've talked quite a bit. Does the thing actually work? So I'll present some experimental results demonstrating how this actually performs in practice. So for this, I used a duplex printed page, the page which I showed you original in the two sets of images, that has text on one side, image on the other. It was scanned on a typical desktop scanner, and the gamma, which is the response curve of the scanner, was set to 1 for the scanning. And this really does not matter as long as you can know it or estimate it. You can pre-compensate for it and adjust it. This is scanned at 600 dpi resolution. For in order to get our algorithm to work, we figured out approximate alignment at just one point in the image using a feature point that I'll point out. And we used a 31 by 31 adaptive filter, which is fairly large, and used LMS adaptation with an adaptation parameter of 10 to the power minus 4 listed over here. And a 15 by 15 neighborhood was used for detecting regions in which you have far and single talk. This is the regions in which there is no printing on the front side and there is printing on the back side. So here's the results from this technique over here. This is the text side after you do the cancellation. And you can see that you've eliminated show through in this image, but this was really the trivial one. You could eliminate it quite easily using thresholding too. One thing which you will notice is that this process has not eliminated the background noise. In the previous case, any background non-uniformity was also being eliminated as a result of thresholding, which you're not eliminating over here. You can always threshold this much more mildly in order to eliminate that. And in the projection system over here, you do not see, but in reality, if you look very carefully on the actual images, you can see some small residual artifacts remaining after this. So there is, yeah. This is the more challenging side. This is what you get for the image side when you do this show-through cancellation. So this is showing the effect of cancellation on the image side. And the point to note over here is not only have you eliminated the show-through in the white regions in the background, but also in the light gray regions in the middle of Texas. And so the physical model is what allowed you to estimate exactly how much show-through you have. The simplification using the logarithmic approximation allowed us to come up with a model which made it linear, and the engineering innovation of adaptive filtering allowed us to actually cancel and estimate that as we went along. The complete system shown over here, the 4 images. This is side 1 after correction, side 2, and side 2 after correction. Now you might wonder, how does this actually perform? So you can look at what do the coefficients look like. So you can go back and see how does the implementation relate to the physics of the problem. Now we described h of xy as a show-through point spread function. If this is a show-through point spread function, you typically expect it to be distributed about a central point with some spread about that central point. Well, if you go and plot these coefficients, they indeed do tend to follow that kind of a trend. So what I'm plotting over here is my adaptive filter coefficients. I mentioned this was on a 31 by 31 scale. So this is 31 coefficients here, 31 coefficients here. Roughly here is the center of my adaptive filter. And you can see that I have a fairly well-defined peak and fall off about it. There is obviously not a well-defined analytical form as you might expect from any experimental noise and error. What I'm showing over here is the coefficients after the filter has tracked at one location, and here are the coefficients at a different location in the image. So I'm processing the image as I go along. You can look at the coefficients at any point. And what you will notice between this point and this point is that the center of mass of these coefficients has shifted. And this is really tracking the change in registration between the two images. So it automatically tracks for registration changes as they occur in this. And that's similar to the application of echo cancellation in telephony that you've talked about. Examples from another sheet of paper. So this is something taken from Spectrum. So you see this advertisement in Spectrum almost every month. This advertisement comes out in Spectrum. And magazines are a particularly interesting application of this, because in magazines you have fairly light printing or fairly thin paper, which means a lot more show-through. So what you can see over here is that you have show-through in this region over here. And again, you have show-through not only in the white regions, but also in the light gray regions. And if you look carefully, you will see it in this textured background also. It's masked by the variation in texture over here, but you can see it over here. And in an image like this, you really see that you have these gradations going from white to black. So any kind of thresholding would introduce contours. This is my attempt at thresholding this, the best that I could adjust the threshold. And you will see that what happened in the process of thresholding is this show-through in this light gray regions actually got more enhanced and pronounced. Because the background became white, I made some parts of this white, this became a little more pronounced. Over here you've got these contours and also still have residual show-through remaining in the light gray regions in different parts. So thresholding really does not address this adequately for this particular problem. This is the result for applying the cancellation technique shown earlier. And you will see that now not only have you eliminated the show-through from all the white regions, but also from the light gray regions. Once again, you can look at what do the filter coefficients look like, and again test their validity with your physical assumption. If this is thinner paper, light will spread less in the process, and your point spread function should be confined to a smaller region. That is indeed what you observe. If you compare these filter coefficients to what I showed you previously, the extent over which they are spread out is quite a bit smaller than what you had in the previous example. And again, you are seeing this effect at different locations tracking the change in registration. So what I've talked about so far really looked at this phenomenon of show-through and considered it as a degradation in the image and said, OK, this is a degradation, you want to fix it somehow. I presented a solution for solving this technique, solving this degradation, which can electronically correct for show-through in scans. It's an effective method for correction. It works not only in white regions, but also in light gray regions. And the aspect which I really wanted to emphasize by means of this example was that three elements that I mentioned, physical modeling, mathematical simplification, and signal processing, are all key components. The way I began with this was when I first got introduced to the problem, I thought, wait a minute, this is just like a cancellation in telephony. I can just use adaptive filters to solve it. And I tried adaptive filters to solve the technique, and they would work in some regions but not in other regions, which is when I went back to the drawing board and said, let me see if I can physically model the problem. And once I came up with the appropriate model, the model was non-intuitive because two terms were in density, one was in absorptance. Immediately the system worked perfectly, and this is one of the few examples where that happens. In the next part of the talk, what I'll talk about is whether we can really turn this around and actually use it as an opportunity. So if there are any questions on this part, please feel free to ask at this stage. So in the second part of the talk, I'll talk about using show-through as an opportunity and using it for watermarking, show-through watermarking, which mimics conventional watermarks. So watermarks, I think everybody is familiar with paper watermarks. These are watermarks embedded in the fabric of paper in the manufacturing process. This is what you see in the dollar bill also. Now, they've been around for a long time. I think the first watermarks were introduced in probably the 14th century, and still you find them as commonly used techniques for validation. They're mostly imperceptible when you view the dollar bill. You don't see the watermark immediately, but can easily be detected manually without much apparatus required. That's their beauty. Once you hold it up to a light, you immediately see the watermark. You do not require any external apparatus in order to validate it. They're commonly used today for security in banknotes and also for ornamentation purposes in bond paper and so on. Their big advantage, which I already mentioned, is visual detection and not requiring any equipment. So here's a sampling of different watermarks. And the reason watermarks are so effective as a security technique is that if you look at currency in particular, the feel of currency is different from other paper. They design the paper to be different. And one of the common counterfeiting techniques is to bleach $5 bills and print $100 bills on them. And you can see that in that case, what will happen if you were to bleach, I don't have a $5 bill over here, but the picture of the president would not match Ben Franklin in that case. So you will immediately know from the watermark that this is a fake. So it's a very effective technique for validating the fabric. And the same principle is applied across different currencies. What I'm showing at the bottom is examples of some watermarks from bond paper in different cases. Now, in the more recent times, there's been a lot more work in digital watermarks. And if you look at digital watermarks, the majority of them are directed towards electronic content. If you have an image or a video file that you're going to distribute on the internet, how do you protect it? They're imperceptible under normal operation and again require computer-aided detection in order to detect it, which is acceptable because the files themselves are also electronic, which are going to be processed in some computer. There are a few techniques which address this for hard copy documents. And an example of this was one of the earliest applications of digital watermarking developed by Brazil et al. At AT&T Labs, AT&T Bell Labs. At Bell Labs before it was AT&T or Lucent, before the split happened. More recently, people have done techniques of embedding. Colleagues of mine have done work with halftone correlation. There are others who've used it also. And then people have worked at Purdue. People have looked at joint watermarking, halftoning. At Digimarc, which is one of the leading companies in the watermarking area, they've come up with a technique which is actually robust against printing and scanning. Again, one aspect of these is that they all require computer-aided detection. So you want to detect your watermark, you have to scan the image in somehow and process in a computer. So that's a limitation for these techniques. in comparison to the conventional watermarks where you just hold it up to a light and see it. So in this part, the objective that I'll work with is to try and mimic conventional watermarks using actually digital techniques. And again, you want them to be imperceptible when viewing either side and visible when the sheet is laid against each other. The big plus here again is visual detection without requiring any equipment. So if you look at halftone correlation watermarks, this is a little bit of background related to this. The way they are embedded is that if you want to represent something which is a certain shade of gray, you turn on that many dots on. That's roughly the description of halftoning that I'll use for this presentation. So these both represent roughly the same shade of gray as far as viewing from a distance is concerned. If you do this at fine enough resolution, that works at a smaller viewing distance also. But you can look at this and you can say that I can produce the same shade of gray by different dot patterns. I can use either the same dot pattern. This is the case where these two dot patterns are exactly identical, and their overlay then will produce exactly the same. When you overlay the two, the blacks will remain black, the whites will not change. Or I can choose one in which I have inverted one with respect to the other. So in this case, what is white over here is black and vice versa. Now when you overlay the two, since everything becomes black, you see a clear distinction between these two. So the way you use this in watermarking is that you design a screen, which is if you design a halftone region such that you design the relationship between your dots in the two regions to be identical in these regions and conjugate in these regions. Now when you print this image out, you take this part of the image and overlay it on this. Then in these regions, you will get a behavior like this. And in these regions, you'll get a behavior like this. So you will clearly see the X demarcated. What does this look like? This is showing a simulation of this. Another advantage of this is self-referencing, because they are both printed on the same sheet of paper. You are using the same part to reference itself. Here's an example of this with an actual image. This is the chapel at the University of Rochester. This is our interfaith chapel. And you do this. This is now done digitally with a simulation, which is showing that exactly that the background remains the same gray as we saw before, and you see a darker region in the X. Now you might question whether you can actually survive this process of printing. Well, when you do this with printing and scanning, the processing is more cumbersome, but this is an actual recovery from a hard copy print with these watermarks embedded. Now, in order to do this, though, you have to go through a whole series of processing. You have to go through the process of scanning these printed watermarks, then aligning them, and again you have to do a local alignment because your registration is not perfect in the printing process. So you do this local alignment and then do, which is compensating for the distortion, and then again finally what you have is, in our previous slide, the representation of the watermark is still visual. So you've not gotten away from the visual element, but you've gone through all the processing in between. So there's considerable computational effort for detection, even though the final detection is still visual. So the idea that I came up with was, why not use physics to your advantage? Just print these two watermarks on the two different sides. When you hold them up against the light, they get overlaid. So that's roughly speaking, the idea. But that's simplistic. It doesn't quite work that way. So you automatically overlay these two halftones on the two sides if you look at them and viewing at a light through the paper. But the paper introduces blurring. So if you were to look at this and overlay those two, you see the nice watermark. But on the other hand, if you simulate what happens with this when the light goes through, it actually gets blurred. And because your correlation is at such a fine scale, once you blur it, you do not see any of this. You cannot see the watermark anymore. So what you need to do is develop alternate techniques which can survive and still be visible despite this blurring. That's what I'll talk about in the next part. I mentioned this already. And for this we use conventional clustered dot halftones for mimicking conventional watermarks. What are conventional clustered dot halftones? These are halftones for which the frequency is fixed, and the way you get different gray levels is by varying the size. So if you want to produce, for instance, 50% gray, you will have this kind of a pattern. If you wanted to produce a pattern which was less than 50% gray, these would be smaller dots in between, over here, and so on. And again, in terms of embedding, the concept can be very similar to what we talked about. you can have an identical relationships in region where you want to make this lighter in the watermarked image, and you can have a conjugate relationship in the regions where you want to make it appear darker. Now, how do you embed? Well, one way to embed is to vary the phase of the halftone in order to embed the pattern. And I'll mention this, that one of the techniques which we are presenting at ISIP next week is actually an extension which came out of this work, which actually uses phase shift embedding in halftones using a dynamic technique. So the way you embed this is that you think of a halftone over here, and you can think of the same pattern. So this is serving as your reference. If you think of a pattern in which you change the phase of these dots by a small amount as you go across, these dots are moving down and then coming back up. Now when you overlay these two, you will get a very different relationship in these regions in comparison to these regions. In these regions, the dot all lay on top of each other, so you did not get any increase in darkness. Whereas in these regions, the dot moved away from each other, so things will appear darker than what they appear over here. So what you've embedded in this process is a band, which is lighter over here, darker over here, and lighter over here again. So I'm just illustrating that over here. You have, without the background, the tessellation shown in the background, you have lighter over here, darker region over here, lighter over here, and so on. How does this work with actual images? So here is an example of an actual image with the embedding in it. And you may see some artifacts in this image because of the fact that this is getting resampled as you project it for display. So this is one of the things which you have to deal with when you're dealing with images which are inherently binary. When they get resampled, you may introduce some artifacts over here. This is what you get when you overlay the two. Now, I'll pass around some samples which show this. What I showed you previously was actually a simulation done digitally over here. So this is, again, the same image printed on both sides. Pass these around. And if you will look at it by holding it up against the light, you will see a watermark. Should be visible in the form of a digital X pattern. It's not perfect, but you can see it. Can everybody see one? And once you're done seeing it, exchange it with your neighbor. And look at this. And you will see a very interesting trend, which is that your neighbor's watermarks need not be the same as yours. Did anybody see that in the? And the reason for that is, again, registration is something which is not, you cannot register the front and back sides exactly. So the registration between the front and the back side for your print is different from the registration between the front and the back side for your neighbor's print. What you're actually seeing over here is the phase shift between the one side versus the another, and that's why you see it clearly in the regions where you introduce the phase shift. You don't see it clearly in the regions where you have a constant shift. What are the advantages of this technique? So the biggest advantage is, again, the detection is purely visual. If you look at it, you immediately see it. There is no external aid required in order to detect this. You do not need to scan the page in and run this through a computer detection system in order to get this watermark. Here's an example of this, which is an earlier example than what you see over here. This is what you see in the scan. And over here, you can barely make it out. But if you invert the image, all I've done is 1 minus the image over here. And you can see this out clearly over here. The embedding here was a pattern, was a T, which you see over here. What you're seeing over there is a further modification of this. And I'll mention one more thing, that you can do this at a slightly higher resolution with the appropriate printing system. The one which we used over here was one for generating a larger number of prints, in which case we did not have the right level of control in order to do this for a higher resolution. So you can do a higher resolution than what you saw over here. So to summarize this case study that I did consider in order to support my thesis, was I talked about show-through and duplex documents. In the first part of the talk, I talked about how you may consider this as an artifact which you want to fix. And I presented an algorithm which really requires the different ingredients that I talked about in order to make it work. In the second part of the talk, I also presented a technique which, again, exploiting the physical intuition, could exploit it and use it as a nice application which mimics conventional watermarking. If you're interested, the publications of this are available on my website, both on the correction part and on the watermarking part. In the remaining minutes, I'll mention that again, these are just one example. If you look at imaging, you have a whole series of problems where again this combination of physical intuition with mathematics gives you really a much better combination than what you could do with either. So try and just walk through these briefly, very quickly. One example of this is what is the nature of your measurement error in your system. Often when you're modeling a system, even your part of your model parameters that you know have errors. So an example of this is when you're fitting a line, the way you typically think of fitting a line is y equal to mx plus c. Now, if you fit a line of that type using least squares to a set of points shown along over here, so this is the way most people would interpret this is what I'm showing over here, a series of discrete points which you measured, which are points in x, y. Those are these x's shown over here. And what you're trying to fit is a line to those. Now, what most people would see is clearly a line over here and a series of outliers which correspond to something which has happened over here. So this is actual data from an image processing application developed at Xerox, where they were looking at trying to detect boundaries of scanned images. Well, if the boundary happens to match whatever the background is, you often cannot detect whether there's a boundary there, and you get some outliers there. But in cases where you have a clear boundary, you can clearly detect it. So what do you do? Well, you fit a line y equal to mx plus c, and this is the line that you get. This red dotted line that I showed you, if you fit with least squares. Because you're trying to minimize the perpendicular square distance from these. So if you look at the perpendicular square distance of this from what you would not logically think as this line, the perpendicular square distance of these points will be very, very large. Or rather, not the projected distance over here. If you look at the distance along the y-axis, that becomes a very large distance. The alternative is to look at a total least squares approach, where you say you're looking at really the projected distance along the perpendicular line to the line that you're fitting. And this has applications both in situations where you're looking at blurred images and restoring them, and you have some uncertainty in the measure of blur. This was work which I did while in graduate school. And has applications when you're looking at modeling printing devices, where the data that you're using for developing the model also has errors. When you do that fit, you get the line shown over here. This is the total least squares fit, the green line. Now you can also do the same thing with least squares. So this sounds almost like, it sounds like I'm cheating a little bit. And in some sense, that is true. If you fit a least squares fit which says, instead of y equal to mx plus b, you fit x equal to my plus b, you get the line shown over here. So you can do this with least squares too, but then you need the priori knowledge of which is the appropriate model to fit. Whereas in total least squares, things work much better. You have the appropriate fit in both cases. I'll skip over this example. This again work from graduate study. Another example is techniques in which you are trying to record data on a printed media. And typically you can model these, particularly photographic prints and transparencies, you can model in a logarithmic domain as being linear combinations of densities. That's the physical model. And then you can use set theoretic estimation to try and figure out what actually is this density. So instead of just figuring out what are the RGB values from a scan, you can actually recover estimated densities. It's a very nice application again of something which is using combination of a physical model along with the mathematical technique in order to achieve. What I'm showing over here is wavelength along the x-axis and estimated reflectance along the y-axis, where the solid curves correspond to measured values and the dashed broken curves correspond to estimates using that technique. What kind of things can it be applied to? Well, often when you're trying to calibrate a scanner, you need a target. But sometimes you do not have a target which is matched to your image. In that case, you can use this modeling technique to do a targetless calibration. So that's the application which is mentioned over here. I'll skip over this one too also in the interest of time. Another application which I did not keep this slide for this, apologize. But this is something which is more useful to demonstrate. So let me actually demonstrate this after this presentation. Since this room will allow me to do this, I'll demonstrate this after this presentation. It may not show properly in the projection system. In order to demonstrate this, I need the room to be completely dark because I want to control the illuminant. One technique, this is a technique called illuminant multiplexed imaging. And this is an alternate way of looking at the problem of color imaging. Traditionally, in color imaging, you're looking at how do I reproduce a desired color image under a given set of lighting conditions. So I look at a lighting condition over here and say I want to produce this desired colored image. I'm controlling 3 attributes. To control 3 attributes, I need 3 actuators. So I control 3 attributes simultaneously by using 3 actuators. An alternative which you can do is that you exploit the way light interacts with the colorants and with the human eye in order to get 3 independent images under 3 lighting conditions. So you'll get 3 monochrome images under 3 lighting conditions. What we've been able to demonstrate so far is 2 images under 2 lighting conditions. That's what I'll demonstrate when we are done with this. So it's a single print, but when illuminated under one set of lights, you will see one grayscale image. When illuminated under a different light, you will see a different image. I will try and do this demo after this. It's on my laptop. I did not put that particular slide on the USB key. I apologize. So I will then conclude this presentation with mentioning that signal processing that incorporates physical knowledge of the problem along with mathematical model really provides elegant solutions for a number of imaging problems. And imaging is particularly a rich source of problems in this area because of its natural location in the processing chain. It's at the interfaces between the physical world and the digital representation. Thank you. If you have questions, I'll be happy to answer those.
Any questions? I'm not sure whether we have anybody on the other side. Any questions? Joe?
Okay. Gaurav, one of the
You want to use the
okay.
there's mics in the
Oh, there are mics there.
Okay.
Speaking to those.
Let's hope this one works. Okay. One of the things that you did with the physics of the problem was that you realized that the image on the back was distorted considerably when you had the original scan of the front, okay, but when you took a picture of the back, what showed through was not just a strict transpose. Okay. Another problem which has come up is registering images that are taken at 2 different times there, which may affect lighting, or you're actually looking for changes in the image there. How robust is the system to that? If I try to detect these minor changes, and then what happens when you are looking for those changes as opposed to looking for the similarities?
The system is fairly robust, and that's just by the nature of the adaptive filtering, because the adaptive filtering is automatically estimating whatever changes are happening locally. So this is your estimate of a local point spread function, which is adapting to any local changes. So for instance, a common example of that would be the 2 different papers I showed you. So say, for instance, you had a region, you did a paste up in which you had part of the page on one type of paper, another part on a different type of paper. Well, as long as once your system reconverges to the new parameters, which is maybe a thinner or thicker filter, to speak a little more colloquially, you've again got the appropriate adaptation. And that's just by nature of not a particular design for our particular technique, but just the nature of adaptive filtering techniques. They automatically adapt to the local nature of the system. So if for paper, what is differing between the 2 different types of paper is how much of the light is actually being transmitted through. That is differing between the 2 different types of paper, and it's adapting to that automatically. The technique by itself, the adaptive filtering, is also something which can be applied not only to this problem, but if you think about it, if you have 2 closely related views, you could think of using that technique for registering them too. And one of the students that I co-advised at the University of Rochester actually did that application and demonstrated that it gives you pretty good results in scenarios where you have an appropriate distortion. So the techniques have applications other ways also.
Any other question? Yes.
When you apply this watermarking technique, What is the intuition behind the changing the phase is robust against blurring?
What's the intuition behind changing the phase is robust against blurring? Well, the intuition is that what we are really applying this is with lower frequency halftones. So if you look at the frequency content for the halftones that I talked about in the previous case, the frequency content is much higher, because what you're varying there in order to produce different levels of gray is the number of gray dots that you're placing on the page. What we are varying over here is the size of the dots. The frequency content is more or less fixed by the spacing between them. So there is lesser content at higher frequencies.
Any other questions? Well, if not, let's thank our speaker.
And if you're interested, I can do a quick demo of the other one. Hopefully, well,
I think we're off the air. So
we're off the air?
Yeah.
Okay.
So we can.